In this section, we're discussing partial fractions. Partial fractions are just the process of undoing addition of rational expressions. So if you look at example 1, you see that I'm adding two rational expressions. When we do partial fractions, we are starting with a rational expression like you see in example 2, and we're learning how to reverse it and go back to having two separate fractions like we did over here. Let's read this introduction together. In algebra, we learn how to perform a process, and then we learn how to reverse it. For example, we learn how to multiply two binomials, and then we learn how to factor a trinomial into the product of two binomials. We have learned how to add rational expressions. This section is about how to reverse that process. So before we begin, we will first review adding rational expressions. So in example 1, we want to add the following rational expressions. So this is algebra, probably algebra 2 material maybe. Algebra 1 or algebra 2 material that you're doing in example 1, so this is not the new material. We're just reviewing. When you add rational expressions, you first determine your LCD. My LCD is x minus 3 times x plus 1. Alright, I can draw, I'm going to make this into a single fraction with the LCD in the denominator. And then I know I have to adjust those numerators to keep my fractions equivalent to what I started with. So over here, my first fraction, I've got 3 over x minus 3. That numerator is a 3. And then because that denominator is missing the x plus 1 factor up here, I need to include it into the top. So I would multiply the 3 by the x plus 1, the missing factor. On the second fraction, my denominator is missing x minus 3, so I'm going to bring down my negative 2, and I'm going to multiply negative 2 by the missing factor x minus 3. Now I've got it into a single fraction. I just need to simplify, so I can distribute across the top. That gives me 3x plus 3 minus 2x plus 6. And I can combine like terms, so that's going to give me x plus 9 over x minus 3 times x plus 1. And that would be my answer. So we're in this section, we're learning how to start from the end result and work backwards to having the two separate fractions. That's what partial fractions is about. You'll see I've got a blurb at the bottom. Foreshadowing calculus. In mathematics, it is often useful to express a complicated object in simpler terms. Using the technique of partial fractions, a rational function can be expressed as a sum of simpler rational functions. This technique is used in calculus to find areas of regions. So let's look at example 2. In example 2, we're asked to write the following expression, that should be singular, as a sum of two rational expressions. And I've got 8x minus 7 over x plus 1 times x minus 2. So I need to be able to break this apart into two separate fractions. To do this, I'm going to write the two fractions that I'm hoping to get here. I'm going to put a plus between them. The denominators have to come from these two factors in the denominator over here. So they have to come from the x plus 1 and the x minus 2, because they have to keep that common denominator. So I know that each fraction needs to have one of those factors in its denominator. And then we have to determine what the numerators need to be. So what we're going to do is we're going to put an a and a b in the numerators, and then we're going to see if we can figure out what the a and the b should be to give us our numerators and our new fractions. Now, looking at what we have a new equation. We started out with an algebraic, with a rational expression over here. Now we have a rational equation with the equal sign, so we get to do some new techniques here. Not new ones, but different ones. Anytime you're working with an equation involving fractions, you can always multiply both sides by the LCD to eliminate your fractions. That's nothing new. My LCD is x plus 1 times x minus 2. I'm going to multiply both sides of my equation by the LCD. So I'm going to rewrite it with this extra step this once. I'm not going to write this every time. But I want to multiply the left side by the LCD. So x plus 1 times x minus 2. And I'm going to do the same thing to the right side. Multiply the entire right side by the LCD, x plus 1 times x minus 2. On the left, the x plus 1 cancels and the x minus 2 cancels. The only thing that's left is the 8x minus 7. On the right, of course, you would distribute that LCD, you would distribute this to each term. In the first one, the x plus 1s would cancel, leaving you with a times x minus 2. In the second one, x minus 2 cancels. That leaves you with b times x plus 1. Okay, so not really anything new so far. Now we're going to distribute on the right. So we'll have 8x minus 7 equals ax minus 2a plus bx plus b. Okay, now is where it starts to get a little bit interesting. I think it's fun. Let's group all the looking at the right side, find all the terms that have x and get those together. So 8x minus 7 on the left. On the right, we've got ax plus bx. These are like terms. The a and the b are constants. So we can combine these. We'll just say that they're a plus b times x. So just like you would combine a 7x and a 3x and add them and make a 10x, I'm going to add these and write it as a plus b times x. And then the terms that don't have x, the negative 2a and the b, they need to be combined, or at least put together. So we'll say plus, and then we'll put parentheses, negative 2a plus b. We don't know how much that value is, but we know it's a constant. It's just a number. All right, so just look carefully at what you have. You've got this term, a plus bx, and then you've got a constant, negative 2a plus b over here. Now, if we look at the right side compared to the left side, we know that the left side and the right side are equal to each other. Since they're equal to each other, the coefficient on x on the left side has to be equal to the coefficient of x on the right side of the equation. And the constant on the left side of the equation has to be equal to the constant on the right side of the equation. So that means that we can say we have, if the coefficients of x have to be equal, we can write a new equation where we can say that 8 is equal to a plus b. And the constant on the left, negative 7, is equal to the constant on the right, the negative 2a plus b. Okay, so how did we get all that? One more time. The coefficient of x on the left had to be equal to the coefficient of x on the right. So the 8 had to be equal to the a plus b. And then the constants, the negative 7, those were the terms that did not have x's. The negative 7 on the left had to be equal to this piece over here that did not have x. That's the constant on the right. So negative 7 is equal to negative 2a plus b. If we look at what we have here in red, that should look familiar to you. We have just created a system of equations like we studied in section 8.1. You can solve a system of equations by using either the substitution method or the addition method. So if you want to do the substitution method, you can take that first equation. Let's solve it for a. So I can subtract b on both. If 8 is equal to a plus b, then that means a is equal, and then I can subtract b on both sides, so a is equal to 8 minus b. And then I can use substitution, put the 8 minus b in place of the a in the second equation. So this is just a substitution method. So that gives me negative 7 equals negative 2. Substitute the 8 minus b for the a, and then plus b. So if you were comfortable with systems of equations in section 8.1, you'll be okay with this process here. Notice you're now working with an equation that has a single variable. So that's easy to solve for b. We can write -7 equal -16 plus 2b plus b. Add 16 to both sides, so you'll have 9 equals 2b plus 1b is 3b. And then divide both sides by 3, so we get 3 equals b. Now that we know what b is, it's easy to solve for a if we just use back substitution up here. So I've got a equals 8 minus b, so that means that a is equal to 8 minus 3, so a equals 5. I probably shouldn't really put, this is not my final answer, but I am putting a box around it just to make it easier to find. So we got a equals 5, b equals 3. We just need to put those numbers back into what we had up here. So our answer is going to be 5 over x plus 1 there. And I apologize, I've got to move it all around. 5 over x plus 1 plus, and we got b equal to 3, so 3 is going to go in here. So it's going to be 3 over x minus 2. Okay, so are we clear on how we got that? And again, I apologize that I'm having to move my paper all around. It took up quite a bit of space to go through this problem. We found that a was equal to 5 and b was equal to 3, so we just substituted the 5 in for our a and the b and the 3 in for our b, giving us a rational expression of 5 over x plus 1 plus 3 over x minus 2. These problems really are not hard. They just have a lot of steps and they tend to take up a lot of space in your work. So you have to be very organized as you're going through these, but if you can be organized about it, you can do these problems. Before I do example 3, and this is part 1 of section 8.4. I'm only going to do the first 3 examples in the notes today. Before I do example 3, I want us to look at some steps that we need to make sure we know how to do. So let's read through this strategy on the 3rd page of your notes. So for decomposition into partial fractions, to decompose a rational expression n of x over d of x into partial fractions, use the following strategies. First, if the degree of the numerator is greater than the degree, if the degree of the numerator is greater than or equal to the degree of the denominator, use division to express your fraction as the quotient plus the remainder over the divisor and decompose the resulting fraction. We're not going to do one like this today, but it will come up a little bit later. Second, if the degree of the numerator is less than the degree of the denominator, factor the denominator completely into prime factors, so that's what we've done so far, that are either linear, meaning they're ax plus b, or quadratic, ax squared plus bx plus c. So what this is saying is that if the degree of the numerator is smaller than the degree of the denominator, factor your denominator as far as you possibly can. Both of the examples we've done so far had already been factored, or they couldn't be factored. But if your denominator can be factored, then you have to do that. And then for part 3, it states for each linear factor of the form ax plus b to the n, the partial fraction decomposition must include the following fractions: a sub 1 over ax plus b plus a sub 2 over ax plus b squared, etc. So what is this really saying? If you factor your denominator and you've got, let's say, you've got a linear factor, so that means you've got like a 2x plus 4, maybe let's say 2x plus 3, and maybe it's being squared. Well, if you've got a term that's being squared, when you set up your partial fractions, you're going to need to include each power of that linear term. And I'll show you what that means in the next example. Part 4, for each quadratic factor of the form ax squared plus bx plus c to the n power, the partial fraction decomposition must include the following fractions. All right, I'm not going to read through all this stuff. All this is saying is that if you've got a factor in your denominator that will not factor beyond a quadratic and it's being raised to a power, first of all, if you've got a quadratic factor, meaning you've got an x squared, you're going to have to do a linear factor in the numerator. And this is another type that you're not going to see today. I'm going to do it in the second video. So we'll have, you'll see that. I want us to practice before we get to this part. And then step 5, set up and solve a system of equations involving the a, b, and c. So that's what we've seen that part. So we're going to keep these rules handy as we go through these. Looking at example 3. In example 3, we have a repeated linear factor. That just means that we've got an x, this x plus 3 in the denominator is being squared, so it's being multiplied more than once. We want to find the partial fraction decomposition for the following rational expression: 3x squared plus 17x plus 12 over x minus 1 times x plus 3 quantity squared. So this time I'm going to, first I'm going to need 3 fractions this time. Because one of these factors is being raised to the second power, I've got to show that in my partial fraction decomposition. I'll start out with x minus 1 for my first denominator, and then I'll have x plus 3 for my second denominator, but then I have to have x plus 3 quantity squared to match this highest exponent here in the third denominator. Because all of the denominators are linear, meaning they just have x to the first and there's no quadratic, there's no x squared, that means I can just use constants for all of my numerators. So that's not too bad there. We just have this third term down here with the x plus 3 quantity square. And then we know that we want to multiply both sides by our LCD. So let's put a note. Well, first, yeah, we're gonna multiply both sides by our LCD, which happens to be x minus 1 times x plus 3 quantity square. Notice in the LCD, I didn't list everything I see in the denominator because this x plus 3 quantity square includes this denominator of x plus 3. So my LCD is x minus 1 times x plus 3 quantity square. If I multiply both sides by that, when I multiply the left side by the LCD, the only thing that's left is the numerator. So I've got 3x squared plus 17x plus 12. Then I multiply a over x minus 1 by my LCD. When I do that, the x minus 1's cancel, leaving me with a times x plus 3 quantity square, or x plus 3 times x plus 3. When I multiply this middle term by my LCD, one of the x plus 3 factors cancels, so I'm left with b times x minus 1 times x plus 3 to the first. And when I multiply the last term by the LCD, all of the x plus 3 factors cancel out, and I'm just left with c times x minus 1. Okay, so this long piece here is the result of me multiplying both sides of this equation by the LCD. Make sure that you see where everything came from. I know it's a lot to look at, but it's not that difficult to see where I'm getting all these terms. From this point, we need to work on simplifying the right side. We need to start distributing and combining like terms. So this is going to take a few steps. If you want to do this in some scratch work on the side, that's fine. I'm just going to bring mine down, and I'm going to FOIL the x plus 3 times x plus 3. That's x squared plus 6x plus 9. And then I've got b. I'm going to FOIL the x minus 1 and the x plus 3. That gives me x squared plus 2x minus 3 plus, and then I can distribute that cx minus c times 1. Okay, bringing this down again, 3x squared plus 17x plus 12. I can now distribute my ax squared plus 6ax plus 9a plus bx squared plus 2bx minus 3b plus cx minus c. So this is the result, oh I'm sorry, there it is. I'll read through that again. So after I distributed the a and the b, I'm left with, on the right side, ax squared plus 6ax plus 9a plus bx squared plus 2bx minus 3b plus cx minus c. And now we're going to start grouping the find all your x squared terms and combine those. So you're going to have parentheses, you've got the ax squared, the bx squared, so you can write that as a plus b times x squared. Now find all the x, just the x terms. So you've got 6ax, 2bx, and a cx. So I can write that as plus parentheses 6a plus 2b plus c times x. And then what are the constants? The constants are the terms that have no x's at all. So that would be the 9a, the negative 3b, and the negative c. So plus 9a minus 3b minus c. That's going to be our constant term there. Can you see how you've created this quadratic, or how this is the in the quadratic form, matching the left side? Let's bring down this equation on the left. You've got 3x squared plus 17x plus 12. Okay, so you've got x squared on the left and x squared on the right. Because the equations are equal, that means that the 3 here is equal to this a plus b. So you can set up an equation, 3 equals a plus b. The linear terms, on the left side you've got 17x equals 6a plus 2b plus c times x, so that means that 17 equals 6a plus 2b plus c. And what about the constant? For the constant, I've got 12 on the left equals, and then my constant over here was the 9a minus 3b minus c. Okay, so this is my system right here. I'm going to solve this for a, b, and c. Now, I know you got 3 variables but it's not that bad, because this first one we can solve for. Let's solve the first equation for a. So that would become a equals 3 minus b. And then I can substitute 3 minus b in for each a here and here. So that's going to become 17 equals 6 times 3 minus b plus 2b plus c. 12 equals 9, and then put in parentheses 3 minus b for the a, and then you've got minus 3b minus c. So now we're down to just a system with 2 equations. We can distribute here, so we'll have 17 equals 18 minus 6b plus 2b plus c. 12 equals 27 minus 9b minus 3b minus c. I can combine like terms on the right side of my equations. So we've got 17 equals 18. Well, I can subtract 18 from both sides. 17 minus 18, it gives me negative 1. Okay, my whiteout's not wanting to work for me. Alright, so I've got, just bringing it over, I'm going to subtract 18 on both sides. That's going to give me negative 1 equals, and then negative 6b plus 2b is negative 4b, and plus c here. My second equation, I'm going to subtract 27 on both sides. So 12 minus 27 is negative 15. Negative 9b minus 3b is negative 12b minus c. But this system here is easy to solve. I'm down to B and C. I'm down to two variables. And if I add these together, my C's are going to cancel out. So I'm going to add these. That gives me -1 minus 15 is -16. -4 minus 12, that's -16B. And the C's cancel. So now it's looking a lot better. If I divide both sides by -16, I get B equals 1. And back here, I had that A was equal to 3 minus B. So that means that A is equal 3 minus 1, or 2. And now that I have A and B, I can find C pretty easily. Go back and find an equation that's got C. So like maybe you might choose this one, for example. So I could say 12 equals 9 times A is 2 minus 3 times B is 1 minus C. So I'm just substituting 2 here for A and 1 here for B to give me this equation. And I can solve that for C. So I've got 12 equals 18 minus 3 minus C. 18 minus 3 is 15. And then I can subtract 15 on both sides. And that gives me -27 equals -C. So C equals +27. Double check. I don't remember that number. Okay, something's not right on that one. How did I get that? So my A is 2, my B is 1. Okay, that's correct. And then I went back to this equation where I had 12 equals 9 times A is 2 minus 3 times 1 for B minus C. 12 equals 9 times 2 is 18 minus 3 minus C. 18 minus 3 is 15. Oh, I see. I messed up right there. I subtract 15 on both sides, and I wish I had my white out, but I don't. Let me see if I can get it to do anything for me. I think it's empty. There it goes. Okay. It's a mess, but okay. So back here, I want to subtract 15 on both sides. If I subtract 15 here and here, I've got -3 equals -C. And then if I divide both sides by -1, I get C equals +3. So my answer for this, and I know I'm out of space, my answer for this would be, I think I can squeeze it in down here. Going way back up to the original, you can look. I'm going to let you look at the top of your page. It was A over x minus 1, so that means I've got 2 over x minus 1. Then it should be plus B over x plus 3. B is 1, so I've got 1 over x plus 3 plus C over x plus 3 quantity square. My C is 3, so 3 over x plus 3 quantity square is my answer. There. So my answer was 2 over x minus 1 plus 1 over x plus 3 plus 3 over x plus 3 quantity square. This is as far as I'm going for now. I think this is enough, and then we'll break this up over 2 days and work on it some more in the next video. So that is it for now. Thank you, and we will practice these in class.